Let's start. So let's see, week before fall break. Are you all ready to sort of are you going to decline towards the holiday? Yeah. It's a bad time to start a new topic, but it's a very cool topic, so I'm sure you'll all be excited. At least I'm excited for it. I'm just curious. So I try to put up notes ahead of time for the lectures. How many of you sort of skim the notes ahead of time? I'm not looking for a yes answer, I'm just curious.
So, I didn't this time, but please keep doing that because that is the goal.
Okay, the goal is to do it. So there's a lot of aspirational things here. So some of you put up read the skim the notes online ahead of time, right? There was some very half-hearted hands, so I wasn't sure. Can we do it again?
Really fast skimming.
Sorry?
Really fast.
Really fast skimming. The reason I'm asking is because a lot of what I do tries to capture what's in the notes. And one would think, we're in the 21st century, it's a waste of time. I'm not reading the notes every time. Why should I sit there and blabber the same stuff? But it looks like you're not actually reading the notes, so maybe it's a good thing. But do you find that, after you've heard the lecture, you go back and read the notes and they're the same, this is annoying to you, or is it a good thing?
It's a good thing.
Is it a good thing?
Yes.
People who think it's, I should be doing something different, and anyone knows how to read and you could just read the notes anyway. What I'm trying to figure out is, there was a time, 30 years ago, whatever, when, if the lecturer was teaching something, you had to pay attention because there was no other way to find out what they're talking about. And now, pretty much everything I'm telling you is available on the web in 10 different ways. Right? And there are probably people teaching it way better than I can as well. So it's not as if, you have to be here to listen to the stuff. So the only hope I have of keeping your attention is if I'm doing something that's of value, right? And so hence my question. I give you the notes, I ask you to read them. And I will kind of follow the notes just to make sure that there's some consistency. But if you feel that what I'm doing exactly mirrors the notes, then I should try to do something different. Or try to add more to it or do something else. But if you feel like it's good to have the repetition, to read it and also to hear it, then what I'm doing is okay. And so that's what I'm trying to get at. And if you don't feel like answering right now, you can also email me later on. I'm just looking for ideas of what you think is working for you. Okay? Yeah.
I tend to understand the notes better after you lecture, so.
Okay. So having both hearing it, seeing it, and then reading it helps. All those things put together help. Okay? That's a good suggestion. Good observation. Like I said, you don't have to answer me right now. If you have any thoughts, you can email me, or you can tell the TAs and tell them not to tell me who said it, but just send anonymous feedback, and that also works very well. So they'll happily tell me that people said this, and I want to ask who said what. So, but please feel free to give feedback in that way. So just to make sure we're all getting what I want to know. Okay. So today we've now covered 4 basic algorithm design primitives, 3 of which you've probably seen before, and some of them, and one which is relatively new to flows. Today we're going to start another primitive which is actually quite different from the ones you've seen before. And to understand what's so different about it and why we should care about this, let's sort of start by understanding what it is that we do when we design the opposite of an algorithm, but a deterministic algorithm. So a deterministic algorithm, or an algorithm as you've seen so far, is one where you give it a set of instructions and it does something and it gets an answer. And then it's your job to make sure that it always gives the right answer. It's also your job to figure out how long it's going to take and make sure it's doing things in a reasonable amount of time. You don't want to design an algorithm that takes too long. And so the way we measure the quality of an algorithm, assuming it's correct, because if it's not correct, it's just not correct, is to measure its complexity. And so we say something like, if we have an algorithm for a problem, so let's say we have some problem P, and we have some algorithm that A solves P correctly. So we can look at the running time of A on any particular input. So we might say, okay, there's a running time of A. So let's say TAX denotes the running time of A on a particular input X. And we might say that the running time of the algorithm, right? So we might say the overall running of the algorithm is something like, in the worst case, TA of n on any input of size n is equal to the worst case. So we take the max over all inputs of size n, TA, right? And this is what we call the worst case running time of this algorithm, right? And we say it's worst case because it's taking the maximum over all possible inputs of size n. And the reason we want to say input to size n is because we like to parameterize this thing by a function of n. We want to say, okay, this algorithm runs in n squared time. What it really means is if you look at all inputs of size n and take the worst possible situation, that will take n squared time. Right? Yes?
It's the probability that it is.
No, there's no problem.
There's no problem. Yeah.
It's a deterministic algorithm.
Yeah.
Okay? And we've already seen that before. Suppose, though, we want to talk about, so a common complaint, and a valid complaint, when people study algorithms or think about algorithm design is that this worst case is annoying. And the worst case is annoying because you're basically hedging against, something that may never happen. Right? Who is there sitting there thinking, I will give you a worst case input, boom, and then that's the problem. Well, we think there are. That's the world I live in, there's always someone there doing that. But in the real world, or the allegedly real world, my world is pretty real too. So in that world, you don't think there are people out there doing that. Of course, there is one place where they are, by the way. Can you even think of a place in the so-called real world where people actually are going, worst case input?
Interview.
White hats?
Interviews, that's a good place. Interviews, they're definitely giving you worst case input. That's for sure. What else?
White hats and black hats?
White hats and black hats, a perfect example. One of the reasons why cryptography has sort of transitioned from sort of a theoretical thing to something out in the community is because there are actually people trying to break it in every possible way. Right? And you've taken, if you're taking Tammy's seminar, you hear more about all the different ways in which you can break security, not just by, by being faster or clever, but by finding weird ways around it. So worst case is important. But in many problems, it's not, it might be overly pessimistic. That's concern, that you are unable to tell two algorithms apart because they are, because they're being one is being overly pessimistic towards runtime, but actually it works really well. And the other one claims to work better, but actually isn't that much better. If one algorithm takes, n squared time on one input, always works in linear time. By worst case analysis, it's going to look worse than an algorithm that always takes, n to the 1.5 time per run. Because, except for that one particular. So there's always a lot of complaint about this. And so if you work, for example, in machine learning, a lot of your work will be, well, assume the data is drawn from a distribution. Assume the data is being picked from a distribution. At which point, you can now talk of the runtime not as a number, but as a random variable. And I did, so T.S. John actually put up some nice links to basic materials of probability. What I found in the past is that, that all of you have taken probability of, or if you have at some distant point in the past, and its memory is fading rapidly, and suddenly now you have to deal with it all over again. So if you might find a refresher course on probability helpful, things like what is probability, what is a random variable, what's expectation, what's variance, what's independence. I will not go into that here. I will basically assume you know these things. Because it would take a whole course of the material to cover that again. But there is if you go to the links, there's a short refresher, there's a little longer refresher, and there's tons of stuff on the web to help you. And in fact, Jeff Phillips is teaching a class on that right now. Okay, so if I want to say that, okay, I have some sense of a distribution over my input, and that is a better way of characterizing the real behavior of this algorithm, I might replace this expression by something different. I might say, okay, so let's say, let x, and this is a notation I will use often, let x be drawn from some distribution D. That means I have some distribution D and I pick x from it. Now there are many kinds of distributions. The obvious one is uniformly at random. But that's not the only kind. I can pick any kind of distribution I want. So once I have a distribution, I can now say that the average case, so we'll call it T average of A at n, is now not the max over all points, but is the expected value over x drawn from D and x equal to n TA of x. So this E means expected value. It's the average. Right? So what you're saying is that the process you could think of as saying, I pick x set at random from the distribution, whatever the distribution happens to be. I run it on the output. I measure the time, I write it down. I pick x again, do it right down. I do this infinitely. And I look at the average of all the values I got. That's my expectation. So you could define the algorithm runtime in this way, but then you run into a problem. The problem you run into is, well, what distribution do I pick? Do I pick a worst case distribution? Do I pick a best case distribution? Where is my distribution coming from? Do I know what my distribution is? These are all hard questions. And again, if you take a machine learning class, oftentimes you will say, let's assume the data comes from the distribution, let's make some reasoning model. That's not what we're going to do here. we're going to deal with the issue of worst case inputs in a different way. Not by asking the input to be probabilistic, but by saying that the algorithm itself can be probabilistic. So what does that mean? If you think of your algorithm now as having an extra operator, it's running through its steps. And it's saying, okay, if this, then go here, okay, go here. Add this number, this, you add this number, you do some stuff. But at some point it says, toss a coin. So the algorithm goes, finds a coin, and tosses it. And the coin either says heads or tails. And the algorithm has a step that says, if the coin said heads, go this way. If the coin said tails, go that way. Okay? And it goes over. And then it has a bunch of instructions. Then again it might come across step says, toss a coin. So it gets on the coin and tosses it. And so on, and so on, and so on. So if you think of an algorithm now as running on an input, it's not running just on the input. It's also running on the sequence of random bits that it's going to use. So the same algorithm on the same input could give you different answers. Or the same algorithm on the same input could take longer or shorter time to run. This is what we'll call a randomized algorithm. An algorithm that, in addition to doing all the other operations, is allowed to toss coins. How do we evaluate the quality of such an algorithm? First of all, how do you even tell if it's correct? What does correct even mean anymore? That's one issue. And then what does this running time even mean? That's another issue. Both of these issues have to be addressed. For now, just for a second, let's put away the issue of correctness. We will assume that the algorithm is always correct, but that it might take more or less time depending on what happens with the data and what happens with the coins. In that case, how do we measure the complexity of such an algorithm? So if we do that now, what's going to happen is that, so now our running time is still going to be worst case. But for any particular input, so let's say now that our algorithm is now not a function. So the algorithm doesn't just take an input x, it also takes essentially a kind of input r. Where you think of r as the sequence of all the random bits of x. In that case, you can now say, well, how long does this algorithm take to run on this input? Well, it depends. And we can say that the expected running time over the choice of random bits. So notice now that my expected value is not being taken over the inputs. It's in fact a fixed input. The expectation is being taken over the choice of random points. So in my new process, I take my input, I start my algorithm, and I run it. And at various points in time, it tosses coins, and it ends. I do it again, again it tosses coins, and again it ends. I do it again and again and again, and take the average of these times. This is an average over the coin tossings, not over the input. And then finally, I can say the running time of the algorithm now. Again, as before, is still worst case. But using this one. So notice the difference between this and this. In one case, I am saying I have a deterministic algorithm, and I run it over inputs chosen from a distribution. That's what is typically called average case behavior. What we're doing instead is looking at the worst case running time, but with an expected value of the runtime for any particular input, because the algorithm itself is tossing inputs. And this is the notion of running time that we'll be dealing with in the next few lectures. We'll talk about how to design randomized algorithms. So in my world, when I say randomized algorithm, that's what I mean. I mean that the algorithm is allowed to toss coins. Is that clear so far? Any questions? Yes.
So the detailed, if I run the algorithm and my worst case is after it iterated, can it be bigger than the expectation?
I don't think I understand the question.
So if I run the algorithm with random tossing coins
On a particular input.
on a particular input,
Yes.
the time it takes missing could
It's
be
some distribution.
it's some distribution, but I am coming up with the value at the end, right, which is max of
Over all inputs.
or the all inputs and stuff. I could take more than I could, but still the max is on expectations, right?
Yes.
So can I take more time than the max of expectations?
Yes. Maybe that there's one particular
One
choice
particular
random
choice.
point that makes your algorithm run for a really long time,
Very long.
but it's a low probability event.
Yes.
So its expectation drops,
Okay.
right?
Yeah.
Because if you think of, say, let's say my x is actually an in-bit string. Let me rephrase. Let's say my r, my algorithm tosses coins n times. So it tosses n random coins. So each particular configuration of random tosses occurs with probably 1 over 2 to the n. So even if my algorithm took 2 to the n time, the total contribution to the expectation is 1. Because it's 2 to the n times 1 over 2 to the n. So yes, this could indeed happen. And that's exactly the point. What you want to say is that some stray, chance here and there that causes my algorithm right time to spike should not reflect what is truly. I should be able to handle it in expectation. And I should say though that, I'm doing this in expectation. And as if you've done any kind of class in probability, you know that the expectation is only one way to think about the distribution of a random variable. There's also things like what the tails look like. What is the probability that the runtime is more than something? These are all notions we will introduce slowly over time. So we can get a much more nuanced picture of what the behavior of the algorithm is. Now, of course, you might say, why on earth should I do this? This is causing me extra trouble. Right? Doing all this stuff is giving me it's a pain in the neck. Right? I should only do this if there's some benefit. And the benefit is quite immense. It turns out that for many problems, it is actually quite easy to get a randomized algorithm that runs in a certain time. But it's very difficult, and in some cases impossible, to get a deterministic algorithm that runs in the same time. Now we don't know for sure. So many of you have heard of this P versus NP question, right? Which basically can be translated to English as is it as easy to check an answer as it is to figure out the answer yourself? From grading, I can tell you it's a lot easier to check the answer than to figure it out yourself. So, but that's not a formal answer. But in the case of randomness, the question that you want to ask yourself is randomness truly a powerful tool to have? Suppose I never had any randomness. Could I solve a problem in the same amount of time as I could with randomness? In general, we don't know the answer. We believe that randomness actually does not help you in the grand scheme of things. But we can't prove it. And there are many specific cases where it seems to help you a lot. If only for the fact that the randomized algorithm is very simple, the deterministic algorithm is very complicated to get the same runtime. Yes?
Can you give an example that an algorithm runs with the random variable and without a random variable? How do you introduce a random variable into an algorithm?
Okay, I will show you in just a second. I'm going to work through an example. But if you want a quick thing of this, quicksort. Quicksort of random pivots is an example of randomized algorithm. So you all know quicksort, choose a pivot, separate everything with respect to pivot from lower and upper, and then recurse on each side. Yes? Choosing the pivot is the issue. If you pick the pivot at random, then you can show that it will have a good rank. And we'll see why we think. But there are many examples. So how many of you use hashing? Okay, you use a randomized algorithm. If you want to do hashing and you want to get constant access, you need a random hash function. You cannot give a deterministic function. Because a deterministic hash function can be beaten. Random hash function will, with high probability, will give you constant access, constant size, or expected constant lookup time. Let's see what else. If you ever use any kind of data analysis tool, if you ever used something that, let me think. Well, it depends on the implementation. Yeah, but there are many. You'll start seeing them everywhere. Basically, in this sort of so-called big data world that we live in, you pretty much have no hope of doing anything if you're not willing to randomize. And in particular, if you're not willing to sample. So there's a whole class of algorithms that says, for example, I have too much data. I want to compute something from the data. I can't do it. So I'm going to sample a few elements at random, and I'm going to compute something from them. And that will give me a clue as to what the entire data looks like. And if you think that's weird, every time you answer a poll question, you're subject of exactly that. Every time someone puts out a poll saying, in the midterm elections, this will happen, They're doing random sampling. And they're sampling and they're drawing an inference about the data from the sample. That's another random method. So we'll see many of these. Any other questions? Okay, so let's look at an example. So the example we're going to look at is it's a very simple problem. It's called a nuts and bolts problem. And the nuts and bolts problem is the following. I have, I'm going to try and draw nuts and bolts. Do not laugh. So let's say I have various kinds of bolts. I have a bolt that looks like this. Maybe I have a bolt that looks like this. Maybe I have a really thick one that looks like this. I have all kinds of bolts. Let's say I have n of them. I also have nuts. I have one nut that looks like this. Maybe I have nuts as a center and this, and so on. Okay? Every bolt matches exactly one nut. Every nut matches exactly one nut. My goal is to match them up. But the only operation I can do is to take a nut and a bolt and see if they fit. And either they'll fit or they won't. It'll be fairly clearly done. So this is the operation I can do. I can take a bolt and a nut and I can test them. If they match, well and good. If they don't match, they don't match. And my goal is to match them all. So let's forget randomness for a second. It's not very good. Deterministically, just like a regular algorithm, what to do? Yes?
Can we treat it as a bipartite graph in which we are doing matching problem?
It's a good question. Treat it as a bipartite graph and do a matching problem. Yes. And then what will you have to do? You will have to construct this graph. Right? How will you construct this graph? You have to know an edge. Right? And you will presumably want to put an edge between a bolt and nut if they can match. Is that what you want to do?
That's what the problem is.
Exactly. That's what the problem is in the first place. So we can't use a bipartite. So it's a good idea, but you're right. That's exactly the problem we have to solve in the first place. Yes?
We'll just start checking every bolt against every nut.
Very good. Check every bolt against every nut. Perfectly fine. It'll take what? As you said?
N squared.
N squared time. Good. So check every bolt against every nut. And that's fine. And it works in, so this works roughly N squared. Okay, good. And the question is, can I do better?
You don't have to.
Once you find the match, you can put them aside. And then
So the first bolt you'll compare against everyone else.
yeah.
And the next bolt you'll compare against n minus 1. Okay, so let's write that down. So that's a slight modification you can make. So it'll be n plus n minus 1 plus n minus 2. What will I give you? With a constant, with a better constant, right? You'll get something like n times n minus 1 over 2. So you get slight improvement, but not huge one. We're still stuck in this n squared form. Okay, now. So for now, let's sort of put away the problem of solving the entire thing. Let's look at a single bolt. So a single bolt is going to check against presumably all the other nuts. It's going to take n time. Is there any way we could somehow use randomness to maybe speed up this process? So here's a simple thing I can do. Instead of scanning the whole list to find the match and not knowing when the match would show up, right? So again, if you think of the cackling adversary, I always think of a cackling adversary. Some of the cackling makes it harder, right? So the adversary is always going to make sure your nut, the one you're looking for, is right at the end of the list. And that's why the worst case is going to take n time, right? So suppose you could randomize your choices. The adversary no longer knows which one you're going to pick next, because you're doing this in random order. And that right there is an important insight as to why randomized algorithms work. You have the algorithm that says, I'm going to sort of sort, I'm going to take the nuts and sort and go through them in ID order, right? So the adversary is looking at your algorithm and says, oh, okay, you're going to look at, I'm going to give you an input that makes sure your guy is right at the end. But if your algorithm says, I'm going to toss a coin and decide which bolt nut to pick next, the adversary can no longer look at your algorithm and decide how to make your input look bad, because it doesn't know what you're going to pick next. And that's exactly how randomized algorithms allow you to beat these worst case models. The adversary no longer knows exactly what you're going to do. Like you faked them out. Brendan, can you go that way? Okay. So now, if I say I'm going to pick something at random to check next, so instead of checking the nuts in order 1 to up to n, I just pick a nut at random and check it. Now, if you don't worry about the formal analysis, what do you think might happen?
Take the same nut over and over again.
Well, that you can fix, right? Because what you can do is you can pick a random permutation of the numbers and just go through that number. So then you don't have to worry about picking with repetition. That's what we call it. So let's say we fix that problem. That's a good point. So we fix that problem. You basically randomly reorder the input, and then you just pick in that order. What do you think might happen? What do you expect will happen? Yeah.
I'm thinking of something like the derivative paradox. It's a high chance that you find the answer in half of the bolts, for example.
So you're correct that you have some feeling that you should find it half the time. It's not the birthday paradox, but we'll get to that later. I think there's a very good class around the birthday paradox. Yes.
So with some kind of normal distribution
For what?
for the PP, so somehow we just pick some nuts and not the other.
You want to pick some nuts and not the other nuts.
Yeah.
And you have some distribution over the nuts that you want to pick.
Yeah.
So these are all valid options. So let's, but just to sort of, we want to layer our complexity slowly. So let's start with a simple thing where we don't even think about the distribution, we just pick uniformly. Every nut is equally likely to be picked. Okay? The vague sense is that somehow you should be able to do better. So why is there a sense that you should somehow be able to do better than going all the way to the end? Why is there a sense of that? Too many hands. Yes, go ahead.
Well, the probability of it being at the very end is 1 out of n.
Is 1 out of n.
Yeah.
Exactly. That's a very good point. So if you scramble, so let's think of this way. So let's say I have my board here. Okay, so I have the particular board I have. And I'm looking for which of these nuts, which I'm going to draw as point because I can't draw that many nuts, is my answer. And let's say my answer is somewhere here. This is the one I wanted. Okay? If I just went in order, well, it will show up whenever it shows up, whatever the ID order is. But if I scramble them, there is some chance it'll be here. There's some chance it'll be here, some chance it'll be here, and so on. And if you think roughly, what is the chance that that one you want will end up in the first half?
50%.
There's a reasonable chance it'll end up in the first half, and there's a reasonable chance in the second half. Since you're taking the average of your runs, you expect kind of that on average you won't have to spend more than n over 2 steps taking. Do you see the intuition here? So this is not a proof. I will show you a formal proof of this. But with randomized algorithms, it's good to get some kind of intuition as to why you think this might work. And this can be tricky sometimes. So we have to get some practice with these things. So that's the thinking. Okay, we know that the adversary is going to try and place it at the end with respect to our ordering. But if we scramble our ordering, the adversary no longer knows where to put it. So there's a good enough chance it'll show up somewhere in the beginning. Then I'll be happy. So can we formalize this intuition? So in order to formalize this intuition, we've got to set up some simple notation. So we want to say something like this. So we want to compute the expected running time of the search for a particular nut. Okay? So let's say now, let me do it here. Okay. So let's say the running time to search for a particular nut for the given board, we'll just call it T of n for now. Okay? And so we want to do something like this. So let's say the average value is going to be sigma over k times the probability that T of n. Right? We're saying we want to find the expected value of the running time. The expected value is equal to the probability of a particular value occurring times the actual value. That's the definition of average. So that's what it's going to be. If we took k steps to find it, then k, and that happens with probability whatever. So as long as we can figure out what that probability is, that t of n is equal to k, we're done. Okay? So how do we figure out what the probability that t of n equal to? So let's first make a simple observation that the total number of steps you're going to make. So what is it? If in fact the answer you're looking for is at position k, right? In other words, if the one you're looking for is at position k, then the algorithm is okay. So let's say that the target is the kth nut tested. And the running time you spent, the time you spent is basically min of k and n minus 1. And the reason I'm writing this in this strange way is that it's not just k, because suppose the nut you're looking for is the last one. Once you have only one left, you don't have to do the comparison, because I just told you there's exactly one matching one. So that's why instead of saying if the target is the k, not your time is k, I'm saying if the target is k, the time is min of k and n minus 1, because you don't actually do the last one. Okay? This might be, you might accuse me of being overly precise here, and you'd be right, but let's humor me for now. Okay? And this is going to be a little bit important as we know. Okay? So now we know what that is. So now we need to figure out what the probability of this event happening is. Right? So, please keep on. So what is the probability of picking? So as we said, the probability of picking any particular nut next is uniform, because I picked the distribution uniformly. Right? So the probability, so let's say that k is less than n minus 1. Right? So suppose k is less than, so you know this weird boundary effect happening. So now you're searching. What is the probability that it takes you exactly k steps to pick it? So the probability that it's going to be is going to be exactly 1 over n. Because the way to think about this is that the probability that at that kth step you get it is 1 over n, because that's a chance that actually shows up in the order, random order at that point. And I want to stop and make sure this makes sense to you. What we're saying is that we're picking the next one randomly. So the probability that I stop after k steps is the probability that next item I'm looking for is the one I want. But that's 1 out of n. So it's this. And it doesn't matter what k is. Right? At every step, the chance you stop is 1 over n, because that's the probability of it. Now, if k is equal to n minus 1, the probability that t of n is equal to k, and you take n minus 1 steps, is 2 over n. And the reason is that if your item is either the n minus 1th thing or the nth thing, then you will take n minus 1. Then you'll take this. So there are two chances of spending n minus 1 steps to find the answer. If you're the second last one or if you're the last one, because you don't actually compare them. And now we have enough to compute our expectation, because now we can say something like the Tn is equal to summation k equal to 1 to n minus 2 times 1 over n times k plus let's see, what will it be? 2 over n times n minus 1. That's just applying the definition of expected value. Multiply the value by the probability of it occurring. We just found the probability of it occurring, multiply that by k. So you get this. Now if you sum this up, this basically gives you, with a bit of simplification, so it'll give you something like a few steps later, something like, let's see. And again, I'm not going to go through all the details, it's in the notes. The intuition here is that take the 1 over n out, sum of k from 1 to n minus 2 is roughly n squared, modulo some constant factors. N squared divided by n will be roughly n. But the constants actually matter here, so we have to pay more attention to this. And you get this one too. So what is this saying to you? It's saying that the expected number of steps it takes you to find the one you're looking for, if you order things at random is n over 2. And that's exactly what your intuition is. That it should be better. Any questions? So again, if you're unfamiliar with, if you're rusty with your expectations and you're a bit worried about the calculations, that's okay. Don't focus on the calculations so much as the fact that we reason how we do this. We reason about what the probability of it being a certain value is, and then we compute the expected value based on that. And the intuition is that if you picked at random, there's a good chance you'll get lucky, and that's exactly what's being reflected here. You take half the number of steps. Yes.
In some sense, you have to do a T-max, right? Are you achieving for all the variables the same and then?
Well, this is for one particular input.
Okay.
I'm saying for one board, if I do this strategy, then the expected number of steps I will take with respect to the random reorderings of my nulls is an over 2. Not with respect to any inputs. With respect to the random reordering of my nulls. Because what I'm saying is it's the same input, it's just showing up to me in different order. Because I scrambled it.
But this expectation is only for
the orderings, not the inputs. Again, I think this is the hardest thing for people who come from stats or other areas to get used to, that we're not averaging over the inputs. The input is fixed.
and this is the time to pick for only one element, right? It's not-
For one, yes, it's only for one. For one board to find the answer. We want to verify that our intuition is on the right track. That if we do this randomly, we expect some benefit. As you are probably seeing, this is not going to give me much benefit. Because if I do this for every board, I'm still stuck with n squared over 2. I haven't really gotten very far. But I've made some small improvements on it. So far, so good. There's a somewhat simpler way of doing, well, simpler. I hate, when I say simpler, I always think people are rolling their eyes at me, but okay. So, a different way of doing the analysis would be to do it recursively, as we always should do analysis, right? So the idea is that you check the first item you match against. You always make the first comparison. Either it's good, you're done, or it's not good, in which case you now have to recurse on n minus 1 things. So you could write something like this. There's another form analysis. T of n is equal to 1, because you always make one comparison, plus what is the probability of having to go on to the next step? What is the probability this match doesn't work? It's 1 minus 1 over n. Because the probability of it working is 1 over n, the first match. Probability of it not working is 1 minus 1 over n. But this is a recurrence. This is a recurrence on the expected value. If you simplify this, ooh, that's not how it's simplified. Sorry. You can say something like n times, by multiplying both sides by n, so it'll be equal to n plus okay. And now, if you go up here, what's going to happen? Set. We get a new recurrence. But this we know how to solve. This will basically be something like T of n is equal to n times n plus 1 over 2. So I lost a minus 1 over n factor, but we basically know the same. 1 over n. So there are different ways of doing the same analysis. All right, let's take a 2-minute break. Yes. of failing. It's not matching the process. So this is the funny thing. I was reading this last night. Why is it not one word? Here's the thing. You always have to set yourself around. The first check you make before you talk to someone. In some sense, because you always make it. So it might be right, it might be wrong, but you always have to make the first comparison, regardless of what you did. Sure, but because I'm just talking like that. So I did my and I compared to one of them. I do that first. Then I have to make a decision. Should I go on? Exactly. So it took me a while to figure that out. So I was even confused. I was like, why is that one of So can I start one thing? I think the way to think about it, if it was the case that I would either go that way or go that way, then you would be lost. Whatever it has to be. Because really you're doing that, and then you're again doing the whole thing. So it's not like you do this or that. You do this, and then you do this. And that's why it's an and. Okay. So what? So we want to do. What is the what is the probability that it takes me 8 steps to find my match? So that's okay. So what is the probability that I find a match? What's the probability I find a match? So it's very complicated. Yeah. Say it again.
It's not. Yeah, I think it's $100.
Simplify that.
Somewhere. A day.
And the way to think about this is not that, oh, I failed, I succeeded. It's more like, think of the color of one of the lines, that's your match. Like you scramble them. What is the probability that showed up on this two? They're all equal like this one. So each position is equal to that. That's what it's equal. It's always because it's like one of those things where you think, oh, I've got 7 blacks. Next one should be white. No matter where you are, the probability you see the next step is always going to be something. You can put it up. So you scale it twice. So you do 1 times 100. All cancel. Because think of the possible choices for the number of steps it takes. You take 1 step, 2 steps, 5 steps, up to n-1 steps. But then for the last one, I hate it because you don't have to do the last one. So those are different chances for your answer. Because your answer could be n-1 if it was the so again, your answer could be the n-1 equation or the n-1. In both these cases, the number of steps you take will be not bad. Because you check this and it wasn't working, you know you're in the market. It's again a silly thing. You could ignore that and say, you'd be fine. The answer will be rejected. It's a slight optimization that's isn't the way but I think it's going to stay. If you don't like that, just pretend to stick with it. The answer will still work.
If it's not,
Even though they
Okay. Now that you're all warmed up and ready to go, let's continue. So as I said, we can show this analysis 2 different ways. That in expectation, you only look at half number of elements. That seems like a good thing. But it's not good because if I take n over 2 steps, thank you. If I take n over 2 steps to find 1 element, I'm still taking n squared steps over. It's not really helping. So while I've managed to convince you that randomization helps a little bit, I haven't yet made it worth your while. So let's try to make it worth your while. And let's try to design a different algorithm altogether. Okay? And so here's what we're going to do. We're going to we're going to cheat a little bit. And I'm going to say cheat because I think, hold on a second. Sorry. Yeah. So let's do the following thing instead. Instead of taking one bolt and matching against everyone, and the one bolt, the problem with this algorithm is that in the process of matching one bolt against all the nuts, I have learned who the match is for this bolt. But I have lost all information about the comparisons I just made. Maybe they're telling me something else that's also interesting. I don't know. Right? Maybe maybe there's some useful information that I can use to separate them out in some form. But I've not captured the information. So let's try to capture more information in each comparison by doing this. So the new algorithm will be something like this. So one is pick a pivot bolt. Okay, just like before, pick a bolt. And now you compare against all the other elements. Right? And it'll match one of them. But now what you do is, when you compare them, it either fits or it's too loose, right? So it either doesn't fit or it's too loose if it doesn't match. You put the doesn't fit on one side and the too loose on the other side. Okay? So now I compare against everyone. Right? And then separate the non-matches into, too loose or too tight. Okay? And also, once you do that, you take actually, sorry, let me erase what I just said. Oh no. Really? Compare against everyone, and then once you find the pivot nut, find the matching nut. So you compare the matching nut against everyone. Okay, so you take your pivot bolt, compare against everyone, you find your matching nut. And when you compare the pivot bolt against everyone, keep track of the people who are too tight for the bolt that will loose. And do the same thing with the matching nut. Keep track against the bolts. So now what you get is, you've taken your original set of bolts and nuts, and you've now broken them into two groups. All the bolts and nuts that were small in the pivot pair, all the bolts and nuts that were bigger than the pivot pair. Right? So then you end up with nuts that are small and bolts plus nuts that are big. Right? And then you recursively sum. This might be sounding familiar to you. It's Quicksort. But it's not sorting. Not quite. So what is the running time of this algorithm? Again, this is a deterministic algorithm. I heard n log n. Who said it? Or you know what I said. So I heard n log n. That is actually, well, let's try and analyze. Let's see if it is in fact n log n. So this is again a deterministic algorithm. So we can write down its running time. So what is this running time going to be? It's going to be, so you write down a reference for this. You're going to do something like 2n minus 1 comparisons. The first bolt compares against everyone, and the second nut compares against everyone else. Right? Plus, in the worst case, we don't know what the splits are going to look like. So the worst case, you look for overall k. Well, I should be, sorry. right? Because you don't know what the split would look like. You don't know what the two set size look like. So you look at the worst case, and you look at this. What is the, if you just eyeball this thing, what do you think is going to happen? What's the worst case scenario for this kind of records? The worst case would be when k is equal to 1. Right? So you can rewrite this as so in every step, everything goes into one file.
Can you repeat why 2 minus n is there?
Sorry?
How do you have 2 minus 1? Oh, because you're comparing other.
The actual comparison that we make.
Okay, you can read it up.
So what's the result of this records? Anyone? T of n is equal to something times n plus T of n minus 1. Not n log n. What happened? I thought everyone thought Quicksort was n log n, but it's not.
Worst case.
It's the worst case problem. And now, the question you're all realizing, the solution you're all realizing is, well, what should we do to make this randomized? How might we, so again, let's think. This is a deterministic algorithm. We have to worry about the worst case split here. The split is created by the pivot. By choosing a pivot a certain way, we create a split. If the pivot happens to be, say, the lowest bolt-nut pair, the smallest one, that creates a bad pivot. If the pivot is the biggest bolt-nut pair, it's a bad pivot. And so we're stuck. We don't know what we're going to pick. And so it's going to be like this. And then you think, okay, if I have to beat the adversary, how would I prevent the adversary from giving me trouble? What is the one piece of information the adversary is relying upon? The fact that I chose the pivot. And then I can rearrange all the other inputs to be bad. But if I didn't tell the adversary how I was choosing the pivot, it couldn't do anything. And how do I hide that from the adversary? By picking at random. I pick the pivot at random, and then I see what happens. I don't know yet if this will work. But if this is where the worst case behavior is coming from, that's what I have to beat. Because we kind of informally know, right, that if this is the worst case, that if this is a worst case and this is a worst case, and where are good cases for the pivot to be picked? Somewhere in the middle. And we know from recurrence analysis that as long as you're somewhere in the middle, you'll get somewhat of a balanced split, and that's enough for n log n. So we just need to be somewhere in the middle. So there are lots of good choices for a pivot, and there are very few bad choices. But in a deterministic algorithm, we have to assume the bad choice. But because there are many good choices, that tells us, aha, maybe we can pick it at random. So the new algorithm is going to be pick, pivot, bolt at random. When I say that, I mean pick it uniformly at random from all the elements. I want to get back to your point about the normal distribution, by the way, that you were mentioning about how we could choose that. And in that analysis, we didn't have to. We could just keep a simple distribution and get something back. There are some cases where you have to be very careful about the distribution you pick for the data. Well, not for the data, for the choices of the random of the algorithm. And then things get more complicated. And then you will need a better distribution. But it's easiest to kind of use a uniform distribution first, and then if that doesn't work, you can try to come up with better and better distributions. Okay. So there are some very good algorithms which need, for example, a normal distribution to work properly. Okay, so we pick the pivot at random, and now this whole analysis kind of breaks. Because that max is no longer a max, it's an expected value. In particular, what we're saying is the following, that the running time again, the expected running time, right, is going to be 2n minus 1 at first, because that doesn't change. But it's going to be the average case scenario for the split. Now each split can occur with equal probability. That should be clear, right? If you pick them at random, that's because they're going to be probability. So it'll be something like 1 over n sigma k equal to 1 to n minus 1 t of k minus 1 plus t of. So instead of picking the worst case k, we're looking at the average. Now this is a somewhat difficult recurrence to analyze. It'll take some work. And you can actually hand wave a solution to this. It's not a rigorous solution. But again, like with many of the things involving recurrences, you can get a sense of where the answer should be. And one way to think about this is that, what is the probability that the pivot you pick lies in the middle half of the set of the input? So somewhere between 1/4 and 3/4. What's the probability it lies in that middle region? Half, right? Because it has half the input there. So there's a probability half of picking a pivot that lies in that middle region. Right? So suppose you pick a pivot that does in fact lie in that middle region. And the analysis is best to get them right, otherwise it causes more confusion. Yeah. So roughly speaking, and again this is very crude, you can say something like the running time is going to be less than or equal to 2n minus 1 plus picking the pivot in the middle. Now if you pick the pivot in the middle, what's the worst case scenario, the worst possible running time you can have, if you're guaranteed to pick it in the middle? It'll be at one end or the other of that middle interval, right? It'll be like using the most skew. That means one side will be roughly 1/4 and one side will be roughly 3/4 of size, fraction of the size. So with probability half, you pay this much. Right? And with probability half, you do badly, but you don't do worse than the actual running time of the algorithm. So this is an approximation. This is not a rigorous reasoning about the algorithm. This is in a hand wave. It says, okay, look, with probability half I can do well, and with probability half I give up. So it's not really what the algorithm is doing, but it's worse than what the algorithm is doing. So my analysis is going to be an upper bound. Right? I'm being pessimistic. And now if you solve for this expression, you get something like, you get T of n is less than or equal to something like 4n minus 2, because I cross multiply by 2 on both sides, plus t tilde n over 4 plus t tilde 3n over 4. And this should be recognizable to you. What is this recurrence going to be for t tilde? This is like our median finding recurrence, right? There are two terms. They both add to 1. You can't apply the Markov directly, but I told you if you unroll the recurrence, this will basically work out to as if it was t of n over 2 plus t of n over 2. And this will give you log n log n. So the expected running time, if you pick a random pivot, is n log n, and the intuition should be something like this. If I pick a random pivot, with a reasonable probability, my splits are balanced. And as we've known from records, it doesn't have to be half balanced, it just needs to be kind of balanced. 1/4, 3/4, 1/3, 2/3, whatever you want. And that's the intuition. The intuition leads to this rough analysis, which will be unlocked. Yes?
So when you put half into Tn by 4 plus 3n by 4, you're assuming that half of the times I do better than Tn by 4 plus 3.
Correct. I will do better, that's the worst case.
But that's the worst case. For
Exactly. Exactly. So it's an approximation. We will do a lot of these kinds of approximations when we do this analysis. You never have to be precise. You just have to be precise enough, or you're going to put an upper bound on what you're really doing. You never have to actually be that careful about this. Otherwise, it gets horribly complicated. And I also want to point out that, actually, let me point it out a little bit. Okay, so we have a crude analysis that says, okay, this is kind of okay, this should be roughly in log n. But this analysis is wrong. It's wrong for a big particular reason. We're assuming that the worst case scenario was in fact that.
T of n.
T of n over 4 plus T of 3 n over 4.
4, okay.
That's only true if my running time is a convex function. If my running time in fact was sublinear, if it was say square root n, this would actually not be true. That's actually a good case. The bad case is when it's kind of infinite. This is to do with convexity of functions. So this analysis is actually technically wrong. But it's a good hand wave to kind of give you a sense of it.
Sorry, why you did not?
So I'm assuming that in this case here, that I can give an upper bound on the running time by assuming that it's actually at n over 4 and at 3 n over 4.
Okay.
That is only true if my function is convex. I'm using a property of convexity. And again, this is a subtle point, and I don't want to belabor it. So if this is something that you're not quite familiar with, it's fine to skip. Be that as may, you should probably recognize this is not a formal analysis. I'm giving you a very hand-wavy analysis of all of this. So what I want to give you now is a formal analysis of how you prove this. It's a much more involved analysis, but it's also very interesting because it replicates the kind of analysis you will see as we go on in the next lectures. So even though it's a bit more complicated, it's actually very precise, and it will give you the exact answer. Okay? So having got a sense of this should be n log n, having convinced us of this algorithm probably should work, let's try to actually prove that it works. Yeah.
Is this convex or not?
Well, in hindsight, we know that it's okay, but we didn't know that when we did it, so we can't do it. Yeah. So hindsight doesn't help us in the field. Okay. So let's try to be more precise. And to do that, we need to use a couple of tools. Okay? And so here's what we're going to do. We're going to think of the algorithm as running in a slightly different way. And again, this is a technical reason. It's because the analysis has to be done a certain way. We're going to pretend the algorithm runs in an equivalent but slightly different way. So what we said was that we pick the pivot at random, we split, and then we keep picking a pivot at random and splitting. Right? So let's imagine that each time we pick this pivot, we pick all these pivots uniformly at random in the beginning. Well, we pick it, let me say this again. Let's say that we pick the pivot, we split, then we look at the set we have next. Actually, that's kind of what we're doing anyway. Okay, let's carry on. So I think it's fine. So let us define some variables that will try to describe what the algorithm is doing. Remember that we said we want to compare bolts and nuts, and we want to estimate the cost of doing so. So let's say the bolt B is there's a bolt I is BI, and the nut J is NJ. Okay? So let's define a variable Xij. Xij is equal to 1 if bolt I is compared to nut J. Okay? So we have all the nuts and bolts labeled, and we'll define this variable. For any run of the algorithm, we will know if a particular Xij is 1 or not. Because we run the algorithm, we say, okay, did you compare I and J? Okay, this is 1. Did you compare I and J? No, this is 0. In particular, these Xijs are random variables. There is some probability that a particular Xij will be 1. There is some probability that it will be 0. Right? Can we express the running time or the number of comparisons that the algorithm makes in terms of the Xij? Yes, because if we're saying that Xij is 1 if BI is compared to NJ, that counts 1 to our cost. So the running time of the algorithm I want to think about this for a second. We are taking what the algorithm is doing and we're breaking it down to little pieces. We're saying let's track this particular comparison of bolt I to NJ, to nut J, and see if it happens or not. If it happens, well, we paid 1 unit. If it didn't happen, we didn't. So the total time the algorithm takes is the total number of bolt nut comparisons that we actually made, which is exactly this. Yes? No? Maybe? Kind of? Sort of?
If bolt I is compared to nut J 4 times, would you put Xij is equal to 4?
Do I ever do that? Think of the algorithm. In this particular algorithm, do I ever compare a bolt and nut more than once? I compare a bolt and nut. Either they match, I never compare them again. Or they don't match, this goes to one side, that goes to the other side. And this bolt nut gets put away. That's a good point. I had to make that check. Every bolt nut I compared at most once. So it makes sense to say it's 1 if I compare it and 0 now. Thank you. But now here's a cool trick. I want to compute the expected runtime of the algorithm. And so I want to compute the expected value of t, which is the expected value of this gigantic sum. The property that saves us all, we praise, probability gods for, is that expectation is linear, which means I can rewrite this expression I've taken the expectation inside the sum. And this works regardless of whether the variables are independent or not. It's a big deal. A lot of times you will deal with variables that are independent of each other, that one can affect the other. It doesn't affect expectation. It affects many other things, but not this. So we can do this trick. And here's the weird thing about 0, 1 random variables. Xij is a variable that takes either 0 or 1. So what is the expected value of Xij? The expected value of Xij is equal to 1 times the probability that it's 1 plus 0 times the probability that it's 0, right? Which is equal to the probability that Xij is equal to 1. This is true for any 0, 1 random variable. Its expected value is the probability that is 1. Which means that if I now want to compute this expression here, this is basically the sum over I, sum over j, the probability that Xij is equal to 1. So I've done two good tricks here. One, so the first important observation is to express the quantity you're trying to find, namely the running time of the algorithm, in terms of these kind of atomic random variables, these simpler random variables. Did I compare these things? That have a 0, 1 value, so you can just add them up. The next trick is to use linearity of expectation to say that instead of reasoning about the sum of all these things, I can reason about an individual one and just add up all those things, which makes life a lot simpler. And of course, the third trick is to say, well, for 0, 1 random variables, the expected value is merely the probability that it's 1. So just like before, we're trying to figure out, okay, what is the probability that something happens? Here we have reduced our problem to, what is the probability over the random coin tosses of my algorithm that actually compare this board and this board? Okay? Yes? So far? So our analysis has now meandered its way to that one point there. That's all we have to do. If we do that, we're done. So the question is, how do we do that? So we have to think now. When am I going to compare bolt I and nut J? If you think of all the bolts and nuts lined up in a row. So let's think of all the bolts. So I have bolt, 1, 2, 3, I, and you have N. And then you have nut, 1, 2, 3, and you have J, and you have N, right? When am I going to be able to compare them? Again, this is with respect to the coin tosses of the algorithm that it makes. The algorithm is doing what? It's choosing pivots. It's choosing a pivot, 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 pivot. Can you think of a situation where you can be sure the algorithm will never end up comparing these two things? So a pivot for the algorithm is going to be pick a pair of these things. I'm not going to draw it yet. I'm going to pick a pair. Right? That's essentially what the algorithm is doing. It picks a pivot, does all the searching, it ends up with this thing, and then splits things into one side or the other. Right? Can you imagine these are now in sorted order? Just imagine conceptually these are in sorted order. Right? So this is the smallest bolt-nut pair, that's the biggest bolt-nut pair. When am I not going to compare these two? What would happen for me not to do that? Ever in this particular run in the algorithm? Yes?
If it's opposite, if the nut is small and the bolt is big and we have already divided into two, so we are not comparing within the two groups.
You're not comparing across two groups.
Across the two groups, yeah.
That's a very good observation. So what your observation is that if you already split them off into two sides, you will never compare them again. So let me take that observation further. When will you split them off? What would have to have happened in this picture for you to have split them off into two groups? Sorry? The index of the pivot.
Yes.
Okay, this is good. So our first observation, if they were separated into different groups, we would never compare them. When would they be separate in different groups? If I happen to have chosen a pivot that was in the middle. Make sense? They will not be compared if we choose a pivot that's in between. Suppose we choose a pivot that's outside. Suppose we choose a pivot from here. Does it have any effect on this, one way or the other? Does it make a difference to our eventual ability to compare these two? I mean, in other words, if I chose this pivot versus this pivot versus this pivot, will that make any difference to the ability to compare I and J? It'll have no difference in the algorithm. The algorithm could care less. So which are the things that matter? So similarly, if I choose a pivot here or here or here, will it make a difference to the choice, to the ability to compare these two? No, it won't. The only choices that make a difference are choices in this range. Yes?
Well, didn't we define our pivot pair as a matching pair? You can't pick
Yes.
a bolt and a different nut.
That's right. So when I say pivot, I mean if you pick a matching pair. So that's why I put the bolts most lined up in order. Imagine them in order.
So there will never be anything between I and J. You can't have something that's bigger than I but smaller than J because I and J are equal.
Why are they equal? I and J are not equal. I and J are arbitrary.
Well,
My question is, when am I going to compare both I and not J? When I and J are not the same.
in order to make a split, you need to pick a pivot pair,
Yes.
matching pair.
Yes.
So anything that's smaller than that matching pair will not have
That
its
one.
corresponding part in the other group.
Right. So, but in order to compute the pivot itself, I have to do all these comparisons. The pivot pair compares against every one pair. So, for example, suppose I picked bold I as my next pivot. I would compare against not J in order to find out where my match was in there. Yes? But if I picked a pivot in the middle, then I would never compare I and J. I and J are different from each other. Yes?
I have a similar doubt. Since we are sorting bolts and nuts.
We're not sorting, right? Conceptually sorting. The algorithm is not sorting, we are sorting.
So like what my intuition was like every first bolt is somewhere in person. Like it's matching with first nut. So that is why I'm feeling like I and J should be equal, except for Xij to be 1.
Yeah, but that's the thing. The algorithm is doing whatever it's doing. The algorithm has a bag of bolts and nuts, and it's comparing them arbitrarily. Yes, exactly. That's what I was trying to say. So it has a bag of bolts and nuts, and it's trying to compare them. It is not sorting anything at all. In our imagination, in the proof, we are sorting. To sort of say, let me look at the imagined sorted order that I get at the end, and let me track what the algorithm is doing with respect to this order. We are not sorting. The algorithm is not sorting. Yeah. That's why you will compare I and J or I and different. You have to check to see if they're going to be compared. We don't know if any particular bolt and nut are going to be compared. They could. But let's hang on to the observation we had that the way the way I and J will not be compared is if in our random process we picked a pivot pair that was between where I and J were in the sorted order. The only way they will be compared is when, for sure.
The pivot pair is both greater or greater than I.
Then we still can't be sure. When can you be sure that they will be compared? If the pivot pair is I or J. If the pivot pair was I or the pivot pair is J, you can be in this group. You'll be sure to pick them. So in other words, if you look at the interval from I to J, and you say, what was the first pivot you picked in this interval? If the first pivot you picked was I or J, they will be compared. If the first pivot you picked was not I or J, they will not be compared. What is the probability that the first pivot you picked in this interval is I or J? Well, there are two chances that happen. The length of the interval is J minus I plus 1. So the probability that Xij is equal to 1 is equal to 2.
Excuse me?
Yeah.
If we didn't choose the first time, we won't be sure that it's not compared at all.
Right, so choices that we make outside this interval don't affect what happens inside the interval. They have no bearing. They don't matter. The only choices that matter are choices in this interval, where either you pick the endpoints or you pick a middle point. If you pick a middle point, they won't be compared. If you pick the endpoints, they will be compared. And every other choice merely defers your problem to later. If I pick my first pivot as 2, then the question of whether xi and j will be 1 gets deferred to later. I still haven't answered the question. So this probability is exactly that. I mean, what I'm really saying is that you can average over all the stuff that happens outside. The only problem, that's why this probability will become exactly this. Everything else just gets conditioned out. And again, a bit of probability manipulation is that, but that's the way of thinking about this. So now we're done. The running time of the algorithm. Now you might not think we're not done yet, but actually this is just algebra. You have to basically, for a fixed j, this becomes essentially something in the form 1 over 1 plus 1 over 2 plus 1 over 3. If you want to hand wave it, this is how it works. This is how I do it. Okay, this is variable. This is, if you fix a particular I, this just is an increasing, this is 1 over 1 plus 1 over 2 plus 1 over 3 type numbers. This will be roughly log n. That's what happens when you sum 1 over 1 plus 1 over 2. There are n of these things, the answer is going to be n lot. That's a good hand wave way of solving this. You can actually work on the details, it's in the notes. I'm not going to do it. And this is a formal proof. All the steps have been worked out precisely. I'm not making assumptions about complexity. So again, the steps of the proof, you define a random variable, you come up with the atomic random variables that together, hopefully by summing them, will give you the quantity you're trying to estimate. And then try to look at how to analyze the properties of the local random variable. And in every case, it's slightly different. The thing that's cool about randomized algorithms, if you have to use them, is that the algorithms are usually very similar. In this case, it was pick a pivot at random and do something. All the hard work is in the analysis. The algorithms themselves are usually not that complicated. They're actually quite easy. And that's the good thing about randomization. When you have to implement it, it's very, very simple. But the hard work is going to be to learn how to analyze it. Okay. So, as we go through the lectures of more randomness, I will try again to point out ways to think about when randomness might be helpful. How you might identify how to pick it. In this case, we said, oh, the pivot was the thing the adversary was playing with, let's pick that at random. And in different algorithms, there'll be different ways of doing this. And then hopefully you will learn and get a bit of practice now to analyze these things. Randomized algorithm analysis is hard. It's not that simple. So we'll get some practice at doing this. And later on, we will also see how to go beyond the expected value. So I said the expected values, and again, that may not be satisfying to me. I want to know, well, how bad can it be? And we'll do the same thing, like the probability the right time is more than n squared is very, very small. And you can say much more nuanced statements about this. We will also look at algorithms that are wrong. They will not give you the correct answer, but they will not give it with only a certain probability. And you can say why and how. But the right time will be fixed. The different kinds of algorithms. Okay? Alright, so I will see you all on Thursday.